Okay, what we're looking at here, if we zoom in and take a peek kind of at like this part right here, this is something we had seen when we looked at Gauss's law. And we talk about, look, here's just basically a little teeny chunk of charge dq that's making a little teeny E field dE at point P right there. And so they kind of have this pear-shaped glob that they just call charge distribution. And then the little bit of charge makes a little bit of E field. If we look at what's happening now, they're asking us to look at, there's a length of wire, and instead of having a little bit of charge marked red, now they have a little bit of current length marked red. And so if the current is running this way, the itty bitty part of the current length IDS is creating a little bit of the B field dB that would be directed into the page. If you take your right hand and point your fingers in the direction of the current, you should be pretty easy to convince yourself that the magnetic field at point P would be directed into the page. If you need another visual for this kind of thing, it is right here. So that's another picture for a current carrying wire and then the magnetic field that's going to be generated from that. If we go on to another page, this is a picture sort of comparing and contrasting Gauss's law with the Biot-Savart law. So if you look on the left side, what's in green is that whole dE equation. And if you look, it's 1 over 4 pi epsilon naught, which is just a constant, and then dq, which is that little amount of charge, divided by the radius squared. And if you look at the Biot-Savart law, we've got dB, a little itty bitty part of the magnetic field is produced by mu naught times, instead of having a quantity of charge, we now have a quantity of current length, IDS. And basically it's still 4 pi r squared in the denominator. It's just what's going on with that mu naught. And so before we talk about that, let's talk about epsilon naught, which is the permittivity of free space. It's that 8.85 times 10 to the negative 12th value. That basically describes how electric fields basically decay with space through a vacuum even. And so that's why it's the permittivity of free space. Mu naught is basically that same deal, how magnetic fields get weaker through space. And that's called the permeability of free space. And the value of that is 4 pi times 10 to the negative 7th Tesla per meter amp. I know you might be thinking, look, here's a 4 pi here, here's a 4 pi here. Can we just cancel and make it 1 times 10 to the negative 7th? And the answer to that is, yeah, most of the time, sure. But a lot of times you're going to see the equation expressed with a mu naught in it. So you're probably going to be asked to keep it. And then if you look at, this is sort of like a little physics fun fact here. If you do 1 over the square root of epsilon naught times mu naught and plug in those values, you get the speed of light, which is something pretty cool. So let's see. For us, the next thing we're going to talk about is going to be how to generate that full equation. And I'm certain you all remember when we had done Gauss's law. At first, we did a really long problem, and then we solved it using Coulomb's law. And it was a big pain to solve that way. And we said, look, you can do the same thing with Gauss's law in like 4 lines. And we're going to do that exact same thing here using the Biot-Savart law to solve a problem. And then we're going to come up with a shorter way to do that as well. And so I'm going to start talking about that next. There's like a time limit that I can speak and make these little videos as of now, and I forgot to set the timer. So I'm going to cut this one here and then just pick up in a split second.